Welcome, everybody.
Thank
Welcome,
you.
everybody. We should get started now. I know some people are still looking for seats because we have a full house tonight. So thank you all for coming. Before we get started this evening, we had an extra special presentation to give that is outside of our normal rota for these things. So Dave, do you want to come up and do that?
Sure. I don't know what the extra special gift award is called. What are we calling this? I know we're giving this to the best German astrophotographer in our group. This is the Helen Pillens Award, which is actually our highest award. And we're giving it to Gert. Oh, wow. For distinguished and meritorious service to the amateur astronomical community. Herr Dr. Gert Gottschalk. Bitte Entschuldigung. And Gert is the EAS Director of Instruments, among other things. And he has a spectacular photo of NGC 6820. He asked with some uncertainty, but that's okay, Gert. Uncertainty is woven into the fabric of the universe. Einstein was wrong. Okay, so Gert, would you like to come up and get this award? We'll do the usual thing where we take the pic. Somebody take the picture.
Hold this and
Okay, somebody take a picture. Out of the shot. Rebecca, do you want to get in the shot? You're the president. Okay. Natasha, oops, that's me.
So I'm gonna make the screen black.
Okay, I got too close to you. I have mic too. Did you see his picture of NGC, whatever? It was incredible. He did this with a 10-inch telescope. I gotta show you. Okay, hang on. Yay, Garrett.
when you start talking, that middle switch.
Mhm.
That'll turn all the house lights off.
You want me to do that?
That's his. Is that not incredible?
That's gorgeous.
Look, it looks like you can see the fingers of creation. Yeah, I'm sorry. Okay. Okay, where can I?
No, you're the farther from the speaker.
Oh, the farther from the speaker. Which speaker? Okay, I'm sorry. Okay, so, normal, is this on? There we go, yeah. Okay, most people think I don't need artificial amplification. Normally, when I do a talk like this, or when I introduce a speaker, I should say, I will read from their introduction. But there's a lot there, Natasha. Forgive me. It was fascinating. I promise. I swear to God, I read it all, and I have a bunch of questions already to ask you. But what I do want, I'm just going to try to introduce you very briefly. So first thing is, she is really smart. She went to Harvard, and did you graduate cum laude or any of that stuff? Probably not.
Yes, magna cum laude.
You are cum laude?
Yeah, magna cum laude.
Okay. So she's really smart. You help with the planning of the Vera Rubin telescope
The survey strategy.
when you're an undergraduate?
A little bit.
A little bit.
And then more now. Yeah.
And more now. Whoa. I mean, has everybody been following what's been happening with the Vera Rubin telescope? Oh my God, it's incredible. And so she's really smart. And this is part of my sneaky strategy, which is you get people before they win the Nobel Prize, because after they win the Nobel Prize, they don't return your emails. So for example, I got Saul Perlmutter like 20 years before he won the Nobel Prize. So anyway, and you know what our secret was? Nobody could get him as a speaker. His landlord was one of our members. So that's how we got him. I swear to God. Anyway, so tonight we're having Natasha Abrams speak to us about black holes and about microlensing. And she's working with Jessica Liu and on microlensing. And the question is, how can you detect black holes? I mean, there's obvious ways when they interact with something, but what if they're like all by themselves? You know, for all we know, there could be a black hole between us and Proxima Centauri. How do we know? Well, she's going to tell us tonight how they're doing this, and you're going to tell us some of the more traditional ways we detect black holes as well. And so without any further ado, future Dr. Natasha Abrams.
Thanks for that super kind introduction. And so, yeah, we have the power to discover black holes. from those a few times the mass of our sun to those tens of billions of times the mass of our sun. We have techniques to find them and to understand them. And we'll be talking about some of those techniques today and how finding the black holes helps us understand black hole physics more broadly and how that plugs into our broader knowledge of physics. So what is a black hole? A black hole is a point of immense density, such that it curves the space-time around it. And it's so massive that light can't even escape from its gravitational pull. So a very brief sketch of an anatomy of a black hole is that in the middle, you have some singularity, this point of infinite density. And then further out, you have the event horizon. This is the point past which light can't escape. And this is because of the concept of escape velocity. So when I'm standing on Earth and I jump, I don't go flying off into space. You need something more powerful, like a rocket, to go and escape Earth's gravitational pull. In the case of a black hole, even light isn't traveling fast enough to escape the pull of the black hole. And that's why black holes are black, because light can't escape from them. And so we can't see them. And light moves the fastest of anything in the universe. It's not possible for something to move faster than the speed of light. And therefore, if light can't escape, nothing can. And so we're going to be talking about a bunch of different techniques to discover individual black holes and how these come together in pieces of a puzzle to understand black holes and physics more broadly. So astrophysical black holes come from exploding stars that have reached the ends of their lifetimes. I'll also be calling them stellar mass black holes because these are black holes that are around the mass of our sun, our stars. And so how do we detect these stellar mass black holes? So in some ways, actually, it's harder to detect the types of black holes that we expect to be more common. We expect black holes that are just floating all on their lonesome, not interacting with anything, to be more common than those that are in what's called a binary, so like a star and a black hole orbiting each other, or two black holes orbiting each other. We expect the ones that are just floating all on their lonesome to be more common. And therefore, though, because they're just all floating on their lonesome, they're not interacting with anything, it's harder to find them. And so in the first section where I'm going through the stellar mass black holes, we're going to be going from the ones that are to some degree easier to detect that are less common, less common, to the ones that are more common and harder to detect. So first we're going to start out with X-ray binaries. This is when you have a black hole and a giant star orbiting each other in a binary. That giant star is so big that it holds a hard time holding on to its outer layers. And so when a black hole comes by, it's able to siphon off material and go around the black hole in an accretion disk. All of that material is rubbing together. And this for a similar reason as when you rub your hands together, they start to heat up from the friction. That gas is rubbing together, and it's also going to start to heat up and to glow. And so that's going to emit in a very energetic wavelength called X-rays, right? And so these are the same sets of X-rays that if you like break your arm and you go to the doctor and they X-ray your arm, these are the energetic photons that are going to be released that we can measure these objects. And so about 20 of these were found between 3 and 23 times the mass of our sun, mostly found in the 1970s when X-ray astronomy was becoming widespread. And so next, I'll talk about gravitational waves from mergers. This comes when you have two black holes orbiting each other in a binary. And so as you can see in this artist representation, when you have the binary, sometimes it can lose energy, and this energy is lost in gravitational waves. This causes literal ripples in the space-time, which can be measured. And so when we're looking at the mergers, we're looking at the spiral, the in-spiral of the two black holes. It's starting out fairly far out, and then it comes closer and closer together until the black holes merge. And I'm not sure if this is going to work, but we can try and listen to the actual gravitational wave signal. Okay, I think it is just coming from my computer, so I will do my best interpretation. It sounds whoop. Right, a little chirp. And so that increase in pitch is that basically you start out going slower and far out, and then it speeds up and up and up and up until they merge together. And the wavelength of the gravitational waves, so the space between each ripple gets smaller and smaller and smaller, faster and faster and faster. And that causes what's called the chirp of gravitational waves. And being able to measure that chirp, it allows us to tell us a lot of properties about the black holes. And so what do these black holes actually look like? You have these stretching and contracting of actual space. So when one of these black hole mergers happens, your body is actually getting a little bit wider, a little bit smaller, a little bit taller, and a little bit shorter. But on such a small scale that that you can't feel it certainly, but you're able to measure it. We're able to measure it using what's called laser interferometry. So you may have heard of LIGO, the Laser Interferometric Gravitational Wave Observatory. This is an observatory that's designed to actually be able to measure that change in space that's caused by the gravitational waves. So you can see here, you start off with a laser that's emitted. It goes in, and then the laser light is split in half. It's called the dichroic. And so you'll get two paths of light that'll go to the end of these, I believe, kilometer-long arms, hit a mirror, come back together, and then meet back up. And if there's been no gravitational wave, then if light is a wave, then they'll still be in phase together, the two waves of light that were split apart. However, if the length of one of those arms has changed, then when the light bounces off and comes back together, then it's going to be out of phase, right? Rather than being in phase together, we're able to measure the different phases of light, which tell us about minute changes in the distance of these long arms. And that is allowing us to actually measure the gravitational wave signal. And so here is a graph of the measured black hole mergers. So the x-axis here is meaningless, just for show, but the y-axis here tells you the mass of the black holes that we're merging. So the way that you can read this plot is, let's look at one of these arrows, for example. So this is saying that a black hole about 8 times the mass of our sun, plus another black hole about 12 times the mass of our sun, merged together and formed a black hole about 20 times the mass of our sun. And so being able to measure all of these black holes has not only just been an exercise in measuring individual events, it's been able to tell us a lot about the actual distribution of black holes and the physics that goes into their evolution and creation. And so some interesting things, for example, are that we have these really massive black holes, 100 masses or 100 times the mass of our sun or larger. this was surprising because we didn't think that black holes can get this massive just from a star having exploded and create a black hole. And so there's various theories as to how these black holes came about. Maybe what's called hierarchical mergers. So like other black holes merge together to form the ones that merge to form the bigger ones. And then there's other features in the distribution of black hole masses, such as lots of black holes around 30 times the mass of our sun. And these sorts of things have made us probe and question how we think that black holes are formed and how they evolve. And so next, I'll be talking about astrometric wobbles to find black holes in binaries. And so, these are more common binaries because instead of it being a black hole being really close and merging with another black hole, or a black hole being really close to its giant companion siphoning off material like the X-ray binaries, these are what's called detached binary systems. So these black holes are in a binary with a star orbiting here, but in our lifetime at least, they're not going to be anywhere close to their companion. They're just going to be orbiting around for millennia. And so what you can do is that you can really precisely measure the position of your star. So that's called astrometry, measuring the positions of stars. And you can see that as the stars orbit, if it's orbiting around nothing, then you can infer the presence of a massive black hole there. And so 3 black holes have been found so far using this method, with additional methods as follow-up. And so this is a picture of the Milky Way with the 3, what's called the Gaia black holes found here. And that's just named after the telescope that was used to discover them. And so Gaia is a space telescope that's orbiting Earth and had taken pictures that was able to really precisely measure the positions of millions of stars. And we're able to start to do the science where we can find the black holes. And so the last method I'll talk about for stellar mass black holes is gravitational lensing. As is mentioned, this one's particularly near and dear to my heart since this is what I work on day to day. And it also is the only method that we know of to find these isolated stellar mass black holes that aren't near anything else. And so gravitational lensing is when you have a massive object that bends the light of objects behind it in its line of sight. So for example, here, if you have some galaxy in a cluster and it's bending the light of some other distant object like another galaxy, and so bends it to us, Earth, then you can see distorted images of that distant object based on where the light would be if it were traveling in a straight line. And so this is an actual picture of gravitational lensing, where in the middle you have a giant red elliptical galaxy lensing the light from a blue spiral galaxy behind it, all spread out there. And so in the case of microlensing, rather than looking at galaxies lensing other galaxies, we're looking at individual stars and black holes. So black hole lensing a star, or another star lensing a star. And these are going to be moving with respect to one another on human timescales that we can measure. And so in this animation, you can see here in yellow is the lens, so that would be your black hole. In red is your source star moving by. And in blue are those distorted images of that distant source that come into existence and go away as they move with respect to one another. But usually in microlensing, you can't actually resolve those distorted images on their own. And by what I mean by resolve is, I'll use this analogy. So if I had 2 flashlights and you were standing really close to me, you'd be able to tell that they were 2 individual flashlights. But if you were across a football field, you would just see one long, elongated blob of light, not that they were 2 distinct flashlights. And so something similar is happening here, where you have these two distorted images, but they're just blended together. And so instead, you see an increase and a decrease in the brightness of your background source as it passes by the foreground black hole, and extra light is bent towards us. And so black holes end up leading to longer duration microlensing events. You can think of this as the black holes as having a bigger area of effect because they're more massive. And so the microlensing event lasts for a longer time. And so so basically when we're able to measure that increase and decrease in brightness, that's called looking at the photometry of the event. And you're measuring the light curve, the curve of light. And so if you can only measure the photometry, that brightness change over time, it's actually not possible to definitively say, well, this event was caused by a black hole. And that's because you need to impose a galactic model. Because there's other things that can change, for example, the duration of the microlensing event. So like, let's say you had a really not particularly massive star, but it was just going really slowly. Then it could have a long duration microlensing event that's similar in length to a relatively massive black hole that's moving quickly. And so here's a plot from a paper I worked on where this is the number of events, microlensing events, as a function of their duration. And so you can see that in black, we have the black holes, and in red, for example, there's stars. And you can see that there's actually significant overlap in their duration between the black holes and the stars. And so when you have just a big collection of microlensing events, and we've measured thousands of them, you can then use a galactic model to say, well, this part of the curve of the duration of the events is likely due to black holes. And if the black holes had a significantly different distribution, then you can start to say something about the overall mass distribution of black holes and et cetera, et cetera, et cetera. But you can't definitively say, well, this is from a black hole. But we can do better. And so we can use what's called the astrometric microlensing signal. And so that's, as I mentioned before, measuring the position very precisely. So we can come back to this animation where, again, that yellow dot is your lens, which would be your black hole. And the open red circle is your source moving by. And those blue are, again, the distorted image of the source. But then that filled in red dot there is the apparent position of your source. And you can see that it's different than the actual position of the source. And you can think of this like a different amount of light is being bent around one side or the other side of your lens. And this causes your source to appear to do a little wiggle as the lens and source pass by one another. And if we can measure that change in position along with the change in brightness, then we can actually determine the mass of the lens. And if you have a really massive lens and you don't see a really bright star, then you can be pretty sure that you're looking at a black hole. And so we use this.
Forgive me, I'm not supposed to ask a question. I know this question about orientation. Are we looking down on the?
We're Earth. You're Earth from out here.
Okay. So
Yeah.
It's the optics that's behind.
Yeah. And so this was used to find the first isolated stellar mass black hole. In 2022, Casey Lamb, who was a grad student at Berkeley, led an effort, and a parallel effort was led by Kailash Sahu of the Space Telescope Science Institute, and they both found a black hole about 6 times the mass of our sun. Yeah. And so these were some of the, to circle back, we looked at some of the methods we can use to detect the black holes, where the more common configurations were harder to detect, and these really, these rare but highly interactive systems were easier to detect. And then next, there's actually a gap in the masses of black holes between about 100 times the mass of our sun and 100,000 times the mass of our sun. we don't know of any black holes. If we did, they'd be called intermediate mass black holes. And there's a lot of efforts to try and look for them and a lot of theories as to why there's this big gap. But ultimately, we're not really sure why there's a huge gap in the masses of black holes that we can find. But let's move on to these more supermassive black holes. So supermassive black holes are found at the center of galaxies. And we have a black hole at the center of our galaxy, the Milky Way. So this is an artist's representation of the Milky Way with the spiral arms and a galactic bar and galactic center in the middle. And there's a black hole inside there. So it's called Sagittarius A star. And similar to when we were looking at the astrometric wobbles to find the black holes, we can look at the orbits of many stars around the center of our galaxy and infer there's something truly massive there. And so I'm going to play this animation in a moment, but just to orient you, these dots are all different stars, and that star in the middle there's nothing there that we can see. But this is the position they're all orbiting around and where we infer that Sagittarius A star is the black hole. And so over the course of 30 years now, we've been monitoring the orbits of the stars in the galactic center. And we're able to infer that there's a black hole 4 million times the mass of our sun there. And so in 2020, Andrea Getz, who's a professor at UCLA, and Reinhard Genzel, who's affiliated with UC Berkeley, won the Nobel Prize for this discovery. And so next I'll be talking about the iconic picture of a black hole. Give me a show of hands if you've seen this picture before. Yeah, pretty iconic picture, right? And so this is M87. This is a black hole 6 billion times the mass of our sun. And so that's 1,000 times more massive than the black hole at the center of our galaxy. And so we're going to break down what we're looking at. What's this red glowing thing around and the black in the middle, and yeah, this picture of a black hole. Okay, so this is a NASA animation of this image. And so you can see the red swirling around and the black in the middle. So the red swirling around is the accretion disk. This is the same sort of accretion disk that in the X-ray binary when you were siphoning off of the material from the neighboring companion star. This is siphoning gas off in a much larger scale. And then again, you're getting, to some degree, the gas friction, the glowing of the accretion disk. But it doesn't look quite disky like the artist representation we were looking at the X-ray binary. There's, this thing going above it. There's something going below. It doesn't look like a flat disk. And we'll break down why. So basically, what you're looking at there is that the black hole is actually lensing its own accretion disk. So the accretion disk is going all around the black hole, but then the accretion disk behind the black hole is being lensed. So the top part of it is being lensed up, and the bottom part of it is being lensed down. So if it were, say, purple on the top and green on the bottom, this thing on top would be purple, and this thing on bottom would be green or something. And so that's what you're looking at there. In the middle, you can see the black hole shadow. So we were talking before about the event horizon, right? The point past which light can't escape. And so here you're seeing that the light is not being able to escape past that point. This is actually a little bit different than the event horizon precisely we were talking about earlier, since it ends up being that when the black hole is spinning and other complicated effects, that event horizon changes slightly. Next, I'm going to talk about why this side of the disk is actually brighter than that side of the disk. Brighter and also, what's it called, a slightly bluer color. And so you can see that in the real image. Yeah, so the it's a little brighter over here than over there. And so that's called, that's due to Doppler beaming. And so you may have heard when an ambulance goes by, goes like wee-oh, 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 right? As it goes past you. And so that's due to what's called the Doppler effect. It affects both sound and light, anything that travels in a wave. And so this is because you can imagine that, if I'm in an ambulance and I'm just sitting here, I'm emitting sound waves at some regular interval. But the ambulance is actually moving. And so, it'll emit a sound wave and then it'll move closer, and it'll emit another sound wave and it'll move closer. And the wavelength, so that's like if you're imagining a wave, again, those are the peaks of your waves. It's going to get smaller as I'm moving towards it. And so in sound, that corresponds to a higher pitch. And in light, that corresponds to a bluer light and a higher intensity to some degree. And so, as it's moving towards us, you end up with that higher pitch. And then equivalently, as it's moving away, you're getting a longer wavelength, which corresponds to lower pitch, redder light, less intensity. And so we can see that here. If you're looking at the animation, you can see that this side of the material is coming towards us, towards you, and this side is going away. And that tells us, or that leads to this side being brighter and more intense than the other. And so how do we actually take the picture of this black hole? So it wasn't just a camera that you can go up and take a picture. Instead, it's actually something much more complicated. So this is a picture of Earth, and each dot on here is a telescope. They're radio telescopes. So they're big satellite dishes that are collecting radio light from the universe. And so these are the same radio signals that would come and deliver information to your little radio that you're listening to music to. And each blue line on this graph, or each blue line on this picture, is each pair of telescopes that took the picture. And so each pair of telescopes makes a point in what's called Fourier space. You can kind of think of it like the information space that corresponds to the image. And so then what actually happens, though, is that the Earth isn't still. The Earth is turning. And so over the course of the night, the observed baseline between each pair of telescopes is going to change. So instead of it, you can imagine 2 points on Earth are going to change, and then the observed projected distance between them will change. This leads to drawing lines in these curves in the Fourier space, or the information space. And so from this is actually how they were able to construct the image of the black hole. But as you can see, it's not a full information space, right? There's lots of empty information, but we're able to infer what's going between them by what's already actually measured. But there's a lot of room for interpretation there. And so what they actually did is they split apart the team that was analyzing, going from this to the actual image, into 4 teams, and had them each come up with their software to create the image, so as to avoid the potential bias that could come from making a full image from partially known information space. And I guess with that context, You can look at this image as for what it is, a construction of the spinning black hole from all these pairs of telescopes on Earth. Okay. Next, we're going to talk about the black hole mass relation. So at the center of every galaxy, there's a supermassive black hole. And so similar to how in our own galaxy, we could look at the orbits of individual stars around our supermassive black hole, instead we can look at the collective motion of all of the stars in the galaxy. And so from there, we can actually see that there ends up being a relation between the mass of the black hole and what's called the velocity dispersion, this overall motion of all the stars in the galaxy. And this is the logarithmic by logarithmic style plot for reference. But it ends up actually being a little bit strange, because if you do the math, the central black hole don't actually influence the entire galaxy. The stars that are further out should have a stronger influence on each other than the center black hole does to the other stars in that galaxy. And so, but we still see that the black hole mass is related to this velocity dispersion. And so there might be some other kind of what's called feedback or something relating those two things. And the last method I'll talk about are quasars. And so quasars are these incredibly powerful supermassive black holes. And so these are black holes that accrete so much material from their active rich galaxies that they end up producing these jets that can outshine their whole galaxy and are 1,000 times brighter than the entire Milky Way put together. And so you end up also with these really long jets that, as you can see in this artist's representation, are more or longer than the galaxy is wide. And so we're able to measure these we're able to measure these, discover them, and understand their mass distributions. And so what happens is that you have some accretion disk. It's accreted a ton of the gas from the surrounding galaxy. And then due to likely the magnetic field around the black hole, it's able to accelerate these particles close to the speed of light and produce these really strong jets that we can then observe. And so coming back to this, discovering the individual black holes allows us to piece together the broader understanding. We talked about all of these different techniques. And so they can help us to build a broader picture of black hole physics. So for example, we can see we can learn more about our stellar evolution and how the black holes are formed, mass distribution of black holes, including the number of black holes, which even in our own Milky Way isn't known to an order of magnitude. And so we can learn that way. We can also learn about the history of the universe and ask questions about that, like how did these supermassive black holes form? And that can tell us something about the cosmology and the history of the universe. It can tell us about supernova, like these explosions of stars and their physics, and how that produces the black holes that we see. It raises a ton of questions, and as we continue to discover more black holes, we hope to probe the answers. And I think I talked too fast, but I will leave you with the summary that black holes are these bodies of immense density such that light can't escape. Black holes less than about 100 times the mass of our sun are these stellar mass or astrophysical black holes. And so we can find them via X-ray binaries, gravitational microlensing, gravitational waves, and astrometric binaries. We can also look at these supermassive black holes that are from 100,000 times to 10 billion times the mass of our sun. We can find them using the stellar motion of orbits of stars, radio interferometry, so the picture of the black hole, velocity dispersion, and quasars. Lots of time for questions. Thank you.
Right. Thank you so much. I get to ask the first question because I got the mic. What is, well, I'm, getting my revenge. What is some of your favorite speculation about the missing masses of black holes?
Yeah. So I guess one of the more generally accepted theories is that basically the supermassive black holes, that they weren't necessarily formed the same way that the astrophysical black holes that we see are. And so that early on in the universe, due to the fluctuations in the amount of matter, you ended up with these overdensities and underdensities. And these overdensities might have coalesced to form these supermassive black holes. So that's one potential theory, it's called primordial black holes, I guess, or these black hole seeds that would be produced from towards the beginning of the universe that weren't necessarily as massive as the most supermassive black holes are now, but that these were the seeds that generate the more supermassive black holes.
Well, thank you. Questions in the audience?
Thank you. That was a wonderful talk. I really appreciate it. I got a whole bunch of questions. Let me start with the dumb one first, okay? We infer that inside the event horizon at the center is a singularity of infinite mass and 0 dimensions. We infer that from the physics we know outside applied to what should be inside. But we don't know what goes on inside that event horizon, and there is no way that we can ever know. The only thing that we know that's inside there is physics that's new to us that has yet to be discovered.
Yeah, so
Yeah, I just want to say nature abhors singularities. Okay.
Yeah, so I guess one, part of the really interesting thing about this is that we're probing general relativity. So when we're able to, when we look, for example, at, all right, let me find the right guy. So when, for example, we're looking at the orbits of these stars, people are looking really closely to see if any of the predictions of general relativity, which would also describe the singularities of the black holes and stuff like this, if there's any chance that that's off, right? And so the singularity, understanding the singularities and the general relativity more broadly is important for, tying those things together. And if we're able to see that there is something off about the general relativity that we can measure, then that might imply there's something different about the singularity and what's happening inside a black hole. But if we're able to support it, ad infinitum, then it's likely that, from the ground up, if that theory was right, that, we're able to prove it more strongly.
You'd be measuring all of that from the gravitational motion of the stars that you could see.
Yeah, so both that and also the, this is the example I pulled up, but also people care a lot about the exact chirp that you're getting and potentially what's called the ring down after the gravitational waves merge. That also probes super strongly the general relativistic effects.
All right, I've got mouth devices. Here you go.
If the conditions and the environment and the parameters and everything that you described are changing, how do you get to a constant? How do you define something if everything around it might have evolved or, I mean, there might be stronger gravitational forces or stars or more exploding galaxies. How does that all fit in?
Yeah. So if I'm understanding your question correctly, like, I don't know, I might not take this in a way that I'm not sure you intended, so you can correct me if this is not what you meant. But we care a lot, or especially in astrometry, when we care about measuring positions, we care a lot about reference frames. You would not believe how many days and months I spend on reference frames. And so basically you want to establish really strongly that when you're measuring like the motion of something, that you're really measuring its motion, that you want to know that relative to the other stars and relative to an absolute reference frame, if possible, that you're actually measuring a signal. And it's not trivial. And especially with, though, with Gaia, that's been able to measure the stars really precisely, and we're able to then build a ladder from measuring, like it's able to measure positions of objects that we can measure more precisely by other means, and we can establish a more direct way of doing that, sorry, direct reference frame, then we can be more confident in our other results. But
I get that.
yes.
And I get that. And so what I'm saying is, by definition, things, the measurement, the process,
Yes.
the number, the conditions around that measurement that defines it. What I'm saying is, how do you know that 100 million years ago or whatever, that you're measuring the same thing, that you're measuring the same parameter in the same way, because everything around you may have changed?
Yeah. So I guess it's like, we're still able, I mean, well, I guess I'm also still trying to parse, I think. So like, there's different measurements that are easier or harder to do that might be affected by like cosmology. Like by cosmology, I mean things that are changing not on human timescales. And so most of the methods that I'm talking about are just changing on human timescales. So a microlensing event could be, a few hours to a few years. And so like things aren't changing on the level of, our Milky Way galaxy hasn't significantly changed shape or something like that. There are other measurements that are a lot harder though. You have some people sitting behind me who work on supernova, like the explosions of stars, and those, change on human timescales, but they're happening over a much wider swath of the universe, where the universe has evolved between those times. And so that's something that you have to take into account when you do your modeling to understand it properly. There's going to be all sorts of different systematics that are occurring depending on what length scale and what time scale you're observing. Yeah.
Is there a theoretical minimum size for a black hole?
Yeah, so there's, I think, two ways to answer this question. One is the black holes that come from the explosions of stars. Yes, so that would be about 3 times the mass of our sun. And that comes purely from atomic physics, or to some degree from atomic physics. So like basically a star holds itself up by pressure from the inside of the star having fusion that generates energy. So hydrogen fusing into helium, helium fusing into heavier elements, and so on. Once that star isn't able to hold itself up anymore, or rather that core can become what's called, or let me back up. So what can then happen is that you're fusing heavier elements from hydrogen, helium, and so on, and you can keep going all the way up until iron. And when you have iron, it ends up that you aren't actually producing energy anymore. That reaction takes energy. Then the star ends up collapsing and exploding into a supernova. What's left behind is a really dense core. And so depending on the mass that's left behind, you can have what's called a degenerate core, which can be, in the story that I told, be a neutron star or a black hole. And so the reason why you end up with a neutron star for the less massive and the black hole for the more massive is called degeneracy pressure. So degeneracy is when you have, for example, you have a type of particle that really wants its own address. It wants its own spin, its own mass, its own, et cetera, and its own position. And it really wants that so much that it's going to keep everything else from it. It's not going to allow things to encroach on its space so it can have its own address. And so what happens is when you have a neutron star, which ends up being left behind, these neutrons really want their own address. But it's possible that if you have enough mass, it'll overwhelm that and it'll collapse. And we think that that mass is around 2.5, 3 times the mass of the sun.
Hi, I'm wondering what the theories are on how the mass is organized in a black hole. Is it a bunch of quarks or a bunch of neutrons, or what is it?
Yeah, so there's something called the no-hair theorem, which says that the matter in a black hole, the mass of a black hole, or sorry, the black hole can only be described by 3 numbers. That's its mass, its spin, and its charge. And so we think that there's nothing left behind about what kind of matter it was made out of. Instead, you're left with this object that's just described by those 3 quantities.
We have a question from an online member. What do you think about the notion that the universe is actually inside of a black hole?
Yeah. So if the universe were inside a black hole, then there would likely be a preferred direction and a preferred spin, right? We would see the galaxies and stuff like this tending to go in a particular direction. And we don't measure that. And therefore, it's unlikely that we're in a black hole, or that we're in a black hole so large that it wouldn't be possible in our small portion of the very large observable universe to know.
You'd be tough at a science fiction film festival. You know that.
I have a question here. I'll try to make an easy one because you're getting really hard questions. For your work, what is your favorite data source? Like whether it's one of these space telescopes or ground-based telescopes, where do you like to get your data from? Thanks.
Yeah, thanks. So I'll tell you my favorite source right now, and then I'll tell you my soon-to-be favorite source, I think, which is the Keck Observatory in Hawaii. That's where a lot of our measurements for the finding the astrometric microlensing black holes come from. We also get some measurements, the Hubble Space Telescope, which are also great. But I'm also personally really looking forward to the data from the Rubin Observatory and then the upcoming Roman telescope.
Yay.
Yeah. Especially together, the synergy is going to be so amazing. So one thing that you might not know about the upcoming Roman telescope that'll be launched hopefully in October 2026.
It has to get canceled.
Is that it'll have both really precise photometry and precise astrometry. And so we're going to be able to do really amazing time series, well, of course, I'm really interested in microlensing, but all sorts of different science, especially towards the galactic bulge, where they're going to have really high, like every 15 minutes, they're going to take a picture. And the synergy with Rubin, that's also really cool, is that so Rubin is going to be able to observe the different patches of the sky for longer periods of time than Roman. And so together they'll be able to fill in the gaps with one another. And also, Rubin is going to be able to survey the whole sky or the whole southern sky. And so we can see how the rates of different phenomenon change over the galaxy. And we can start to measure things like the black hole mass distribution is a function of position in the galaxy. Is that different in the galactic bulge versus in the disk? Stuff like this I'm really excited for.
As a follow-up to that answer, I'm wondering to what extent have the research teams built automated tools to look at the data to find the signatures that you are specifically looking for? Because I'm imagining, like, 50 years ago, people looking at these
Yeah.
plates over and over and over again. But there's obviously got to be automation with this volume of data. So
Absolutely.
what's the process of that?
Yeah, so it's not an easy process. I can tell you that 2 weeks ago, I went to a sprint week for the Rubin Observatory where we were sitting down looking at exactly this, the pipelines for alerting on ongoing microlensing events. And so what we did is we actually split into 2 groups to work on 2 different ways of detecting them. So this is going to be hooking up with what's called the alert brokers. So in the Rubin Observatory, all the data for changing sources, so when like a source changes in brightness significantly, they're going to alert on it. And they're going to make that data public immediately, within 60 seconds it has to be. And so those will be sent to the alert brokers. And so we want to be able to tell when when that alert is likely associated with a microlensing event, so that we can potentially follow it up with CAC or HST, right, to be able to really pin down that something's a black hole, for example. And so there's a few different ways you can do it. One is using machine learning. You can train a machine learning model and you can say, well, this is what we expect, microlensing or supernova or whatever other phenomenon you're interested in to look at, and it can try and sift through that data. Another method that you can do is kind of a slightly more traditional way where you do like different cuts on like the quality of the data, making sure, for example, you don't have a periodic signal when you're looking for something that only has 1 peak, or like how correlated your data is over the course of the light curve, the light over time, stuff like this. And then you can start to fit a model to it. You can say like, how well does the model of microlensing fit to this? And so if you have some other event, if you have some other changing object, but it changes in a really asymmetric way, then you can be like, well, that might not be microlensing, stuff like that. Yeah.
Thank you.
Sure.
Against my better judgment, I'm going to give Dave a chance to
I
ask.
think that,
Oh,
had a question.
yeah, go for it. Go for it. Go ahead.
I believe you said that every galaxy has a supermassive black hole at its center. And so my question is, at what point in the evolution of galaxies does the black hole form? I think you said you think it's probably at the beginning. And if that's the case, then does the characteristics of that black hole determine everything else about the galaxy? How large it will end up, how many stars will be in it, and so on?
yeah. So yeah, that is a theory. So that's the theory that I know of the best. That the black hole would come first, and it would shape to some degree the galaxy that you form, or that multiple factors would apply to both. And that might be why you end up with like a relationship between the mass of your black hole and the overall velocity dispersion of your galaxy, or the brightness of the galaxy, or how quickly it evolves, or stuff like this. Yeah, it's likely related.
Thanks. Is there anything in your research that's being utilized by other researchers? Are people coming to you and saying, oh my gosh, this is so fascinating because something I'm doing with like dark matter or some other field?
Yes, exactly. So dark matter, you're actually spot on. So basically, one potential source of dark matter is called primordial black holes. So these are potentially like, you had the fluctuations at the beginning of the universe, these overdensities and underdensities. And so they might have formed the seeds of the supermassive black holes, but they also might have formed like relatively small black holes that are less massive than our sun. or the same mass, or there's actually a huge broad range of potential masses that they could have formed. And so actually the first microlensing experiments were done to look for these objects. At the time they were called MACHOs, massive compact halo objects. And so basically, looking towards the large Magellanic Clouds, where we would be looking through our galactic halo, where it's thought that dark matter is, and seeing if a macho or a primordial black hole passes in front of the large Magellanic Clouds and causes a microlensing event. And if, though it's thought now that a lot of the things that were measured were actually what's called self-lensing, where two different stars in the large Magellanic Clouds actually just lens each other, not necessarily something from our halo. But we're kind of in a more modern context. We're looking now towards our own galactic bulge and saying, well, the dark matter should actually be distributed throughout our galaxy, not just in the halo. And so we've measured so many microlensing events towards the galactic bulge. We could potentially see differences in the model based on, our galactic model. Maybe if there's some population that has a different distribution than what we expect, then maybe that could actually be dark matter.
In the image of M87 that you put up, what is the orientation of the disk? I couldn't quite figure that out.
Yeah. So in the simulation, they have it this edge on, but that's not necessarily thought to be the case here. So there's a few different models. There's what's called degenerate models, which basically two different models that produce identical or near identical images, or certainly that we wouldn't be able to distinguish this with this quality of data. And so it's actually not quite known what the inclination is. Even not by eye, but with the best science that you can do, there's multiple different inclinations that this could be.
Dave?
Oh, great, thank you. Okay, like a bunch of us here, I have a number of questions to ask. So after the formal session is over, I'm going to attack you at the podium as well, as it often happens at conferences, as you all know. The first question I'm going to ask you is one question that little kids always ask me when we do outreach, which is, how close is the nearest black hole? I'm assuming it's one of the Gaia candidates.
It is. So that is, oh man, I used to have this number on the top of my head and now I'm forgetting it. But I think that it's on order 100 or about 1,000 to 10,000 light years away, but I don't actually remember the number.
I think I remember on the order of 10,000, but I've often
Yes.
been wrong, as my wife often likes to remind me.
Yeah, I think that it, yeah, go ahead.
And the second question is, in what direction is it? Because kids always want to know, is it there? Is it there? I'm sorry, Garrett.
Yeah, so it's Gaia Black Hole 2 that is the closest, I believe.
Yeah, well,
So it's in kind of towards the edge of the galaxy. So if you're able to see the Milky Way,
yeah.
this way I believe is the well, okay.
You're
this
pointing towards the Magellanic Clouds.
Yes,
think,
that's
so.
the southernish
Yeah.
part of this, I believe. But what's it called? You may want to double check me on that because I don't actually remember quite the numbers of each.
That's okay. Can I ask another question? Okay. Couldn't we model, I mean, I've often thought about what it looks like if you're just inside the event horizon, right? I mean, can we not stop shaking your head, Garrett. Couldn't we model what it would look like inside there? I would guess, I mean, you have all this radiation that's zooming around, orbiting the singularity. I would guess it's an area of just intense brightness. Is that what the models predict, or are there other alternatives?
Yeah, so this is, purely in the realm of math, not in the world of observation. But it's actually potentially thought that you wouldn't even know when you pass the event horizon. The event horizon is, past this, point that you can't escape. But I guess it's not quite known what would be done with the radiation. And so one, one potential thought is that all the radiation is being accreted and it's going towards the singularity. And so, it wouldn't necessarily look any different than outside the event horizon, especially for a very big black hole, where like there's less what's called like tidal forces that would be like ripping things apart.
So you wouldn't be spaghettified if you're going into a large black hole. Super.
Or you could, it depends on exactly the parameters.
Okay.
Yeah.
Okay, I'll pass this to somebody else.
Any other questions?
It's a really kind of simple question, I think. All right. When you were showing like Sagittarius A star and then the one in M87, is there a sense of what is the diameter of the accretion disks?
Yeah. So basically those two. So I only showed the Event Horizon Telescope picture of the M87, but it's also been done for Sagittarius A star. And those are the only two black holes that have an accretion disk that is expected to be able to be resolved by the Event Horizon Telescope. Every other black hole that we know of for the current iteration of the Event Horizon Telescope would have too small of an accretion disk to be resolved. What's it called? The exact number, again, I don't have it on the top of my head. It's a few it would be less than a parsec.
Oh, it's that small.
Yeah.
Oh.
Yeah, I have one. It's kind of like a fun question. If you're looking at all these observation projects, missions that are being done, could be done, if the fairy from NSF comes to you and say, money is not an objection, effort is not an objection, you have one wish, what mission would you want?
In some ways that one's harder. So I think it's specific. Okay, again, I really like microlensing. And so like I think it would be really cool, or rather I'm gonna do a slight cop out. So there's another grad student in my lab that's working on this mission called Curious that they're applying for. And basically what's happening is that she wants to send a fleet of CubeSats. And so that the entire sky that's observable, at the time of year, depending where the Earth is, would be able to be observed by a telescope. So we'd have, simultaneous coverage, both photometrically and hopefully to some degree astrometrically of the entire sky, so that we can measure the entire transient sky at all times, barring the sun being in the way. Yeah.
Any other questions aside from Dave?
That's discrimination. Can I ask a question? Okay. How many black holes have actually been detected with microlensing?
Just the one. And what's it called? From the astrometric microlensing, the photometric microlensing, like, given the models, like, there's candidates of like 10 or so, but there's a lot of, basically it ends up taking a really long time. The signals can last, 5 to 10 years. And so there's a lot in the pipeline, I will say.
Okay. Okay. Where did you come from?
In here. Is the current belief that all primordial black holes, the supermassive ones, have some spin? And the other question that's part of that is, are they able to measure the spin on the supermassive black hole at the heart of our galaxy through like frame dragging or anything?
So to answer the first part of your question, I believe that most supermassive black holes are thought to have spin, but I guess you can to some degree be informed by that, by the accretion disk and the jets if you're measuring a quasar. But it's also not quite known sometimes if the accretion disk is actually aligned with the spin of the black hole. We, naively would expect that it would be, But there's, some potential like modeling and stuff like this with where you have like a prograde accretion disk and a retrograde spin of a black hole or something like that, potentially. And so for Sagittarius A star, I believe that they are looking for that sort of thing in the like very precise measurements of the orbits. Yeah.
Okay, so is this score? Yeah. I just want to say that I learned two interesting things tonight from you. It's very important. Number one, that a gravitational wave interacts with an electromagnetic wave by tweaking its wavelength, in a sense.
Oh, so I guess it's just changing the length that it goes by. Yeah. So
Therefore, I have to ask, can one modulate an electromagnetic wave to tweak gravity a little bit? Is that okay? Number two, number two is that one can measure a Doppler shift in gravitational waves, presumably by a rotating black hole star dipole moving past it. Is that correct?
So sometimes what we expect with the gravitational waves is if the sources are moving towards each other away or towards us or away from us.
Doppler
So we potentially can measure like that sort of Doppler shift when the whole system is moving towards or away from us.
Okay. Now let me ask the question.
Okay.
The one with the stars orbiting a star, the visible stars. That's the only thing we can measure, their gravitational motion. How can one differentiate between a point mass or a mass that's distributed as long as it's inside the Schwarzschild radius? Newtonian physics says the gravitational field should be the same on the outside.
What's it called? So process the question.
Differentiating between a point mass motion and a distributed mass motion, as long as it's inside the Schwarzschild radius.
So
how does a Newtonian gravitational field measured outside?
So I guess I guess wrinkle here is in how we understand the matter that would be in the black hole. So if you have enough matter, if you had 4 million times the mass of our sun in the Schwarzschild radius of that black hole, then we don't know of like normal types of objects that are different than a black hole that can have that much mass, that dense. By definition, to some degree, that's what a black hole is.
So in other words, the mass divided by the volume of the Schwarzschild radius, not by a point. That's really all we know. And we'll never know anything more unless somebody comes up with some new physics.
What's it called? I guess the best theory we have is general relativity. That's for now.
Other questions?
You have answered my question? Okay,
Go ahead, Dave.
Okay, shoot, he distracted me. I almost forgot my question. Okay, no, please don't. Okay, is this on? Yeah, there we go. So, I was intrigued by your model of, detection of black holes versus number of black holes, that downward sloping line. Do we have any sort of theoretical model as to how many black holes, for example, would be within the Milky Way galaxy? Do we have any sort of predictions at all? Any idea?
We do, but it's wildly uncertain. So we believe
I can accept error bars.
It's believed to be about 10 to the 8 black holes plus or minus 1 in the exponent. So 10 to the 7 to 10 to the 9.
Oh, that's reasonable. 10 to the 7th to 10 to the 9th black hole. So, okay, I got to think now. 10 to the 6th is 1,000,000. So 10 to the 9th is 1,000,000,000. So somewhere around 100 million to a billion, something on that order.
Yeah.
Am I getting? I'm screwing this up.
Yeah, I think so.
Okay, so 10 to the 7th is 10 million, and the stellar population of the galaxy is something on the order of 200 billion.
Yeah. It's like 10 to the 11.
10 to the 11th. So yeah, so it's something like one black hole for every 1,000 stars roughly. Okay. Okay, I've got other questions, but I'm willing to pass it.
Other
back to
questions?
Steve.
Anybody else?
Oh, that was too easy. Actually, the thing is, we should be nice because these guys, we can't do observing because the fog was rolling in, but we can at least show you the telescope.
That'd be great.
Okay, and we'd also show you the facility too. And should we quit
I
here?
wonder, I think this might be a good time to wrap it up.
And then I can
And
ask her questions afterwards.
Maybe a few questions and maybe not keep her all night.
She's an astronomer. She's used to being up all night. Okay, thank you. I'm a Monty Python fan, and now for something completely different. Next month, we're having Professor Rick Nolthenius from, I think, is it UC Santa Cruz? Or no, Cabrillo College, who is an expert on using occultations to determine shapes and various facts about asteroids. So it ought to be a fun talk. And then in September, we have what has been described to me by the late Dr. Ken Lum as the best solar talk he's ever heard. And that's from, he's a scientist at Lockheed. All of a sudden, his name went out of my head. But anyway, but make sure, keep watch. We've got some great speakers coming. And that's all I have to say for now. Thank you.
Thank you. Attended Foxy 4 years. I just want you to know that. I don't.